So folks, we're picking up with our techniques for solving nth order linear equations. And in this section we're going to learn a technique called variation of parameters. That's the goal of this section. But before we do that, I'd like to have the first page be a recap of what we've done so far with the various techniques. So I'll do a couple of key examples and hopefully that'll remind you of what we've learned. So if our equation looks something like this, then solving this, and this is a homogeneous ODE. Why is it a homogeneous ODE? Because it's set equal to 0 there. And here I'm inferring that a sub n, a naught, a1, all the way up to a sub n, those are constants. Specifically, I didn't write them as, say a sub n of x or a sub n of t. So these are not thought of as functions of the independent variable. Instead, they're just, well, that you could, but we're going to consider them to be constants. So when you're trying to solve such a homogeneous ODE with constant coefficients, you simply give the corresponding characteristic polynomial, which I've done here. So here's the characteristic polynomial, and then we find the roots of them, and then we give our solutions accordingly. So let me give you this example here. Here we've got a fourth order homogeneous ODE, fairly complicated looking, with constant coefficients. So the corresponding characteristic equation would simply be r to the fourth minus 4r cubed plus 8r squared minus 16r plus 16 equals 0. And this would take a little bit of time to find the roots to it. You could use a few different methods that you'll practice in your homework. But it turns out that this equation has some roots r equals 2, and that has multiplicity 2, and roots r equals plus or minus 2i. That is, eventually what you could do is you could factor this through some work. You could factor this, let me scoot over a little bit, as r minus 2 quantity squared times r squared plus 4 equals 0. That's how that factors, and so that's where we get the root of 2 with multiplicity 2 and the root of plus or minus 2i. No multiplicity there, but that gives us the 4 roots to the characteristic equation. Great. So once we've got those roots, then giving the general solution is as simple as just saying that y sub t and then knowing how to interpret this. So we'd have y sub t would be c1 e to the 2t, and then normally you would go ahead and do that for each of the roots, right? Each of the real roots, so you would think you would also put another 2t there, but of course those are about as non-linearly independent as you could want, and we showed that a way to get another linearly independent solution was to simply multiply it by a factor of t there. So we do that because this had multiplicity 2, and so we need a factor of t to give us another linearly independent solution that also solves the characteristic equation. And then we have the other two solutions. And normally, how do we write these complex ones? So I'll jot this down below here, but then we'll simplify that. Normally, how do we do complex solutions? Well, if our solutions look like a plus bi, we write it as, this would be c3 e to the at cosine bt plus c4 e to the at sine bt. But in our case, because our roots are strictly imaginary, the a value is understood to be 0, and if a is 0, then that term just becomes 1, and we don't write it. So let me clear that out of the way. And so how do we give our solutions to this? We'd have c3 times the cosine of 2t plus c4 times the sine of 2t. So that was a very quick recap of what we need to do if we're solving a general homogeneous equation with constant coefficients. All we have to do, and our ability to do it, is simply up to our ability to do algebra and find roots of the characteristic equation. That doesn't make it easy, but there's nothing more to add from a differential equation standpoint. Okay, let's see here. So if our equation were to look something like this, and notice here what we have on the right-hand side, and we can, I like to think of that as a forcing function, an external forcing function, and we'll talk about that in our spring examples. But in this case, what we have is a non-homogeneous ODE. and I suppose what I wanted to say here was constant coefficients, coefficients, and I didn't give you enough room for that. It may be possible using this method of undetermined coefficients, provided f of t is comprised of sums of functions whose derivatives either eventually go to 0. So that might be a function like this. Why? Because this forcing function over here, it's if it looks like 3, the derivative of that eventually goes to 0, or maybe something like this polynomial here, 2t squared minus 7t. Why? Because if you take successive derivatives of that forcing function, it eventually goes to 0. So that's one possibility for which this method of undetermined coefficients would work. Or if the function, that forcing function over there, its derivative eventually repeats itself up to constants. So for example, a function like a forcing function like the sine of t, when I take enough derivatives of that, when I take the derivative of the sine, I get the cosine. When I take the derivative of the cosine, ignoring the sine on it, the constant, I would eventually get back to something up to sine. And again, that's what I'm saying, up to constants here. So that's a derivative that repeats itself, or maybe something even more complicated like e to the 2t plus t squared times the cosine of t. That's a sequence of functions, and those terms would eventually, when you take successive derivatives, you'd have all possible derivatives listed, and they'd be repeating themselves. And so you could use this method of undetermined coefficients on them. So again, that method is called the method of undetermined coefficients. And we give the general solution as simply a homogeneous family of solutions plus one particular solution. Okay? A warning about this method of undetermined coefficients: you have to solve the homogeneous equation first. Why? Because when you give your guess at the particular solution, you must make sure that you avoid a guess that includes a solution to the homogeneous family for various reasons. One, that solution will just output as 0, and it certainly won't be linearly independent from that family of solutions. So now you can take a look at example E here. And here again, we've got a fourth order non-homogeneous ODE with constant coefficients. And we want to solve it, but in this case it's non-homogeneous, and we want to solve it using the method of undetermined coefficients. So here is that forcing function on the right-hand side there. Notice that the derivatives of this forcing function eventually repeat themselves over successive derivatives, so we can use this method. Okay. Now, normally, our guess for y sub p would be y sub p equals, and then we need to say, okay, we would take a e to the 3t plus b cosine of 2t, that's a little bit messy there, that's a b, plus c sine of 2t. And normally we'd make that as our guess because the derivative of that first term, it immediately repeats itself up to a constant, because the derivative of e to the 3t would be something e to the 3t, so good to go there. And then cosine of 2t, it has derivatives of sine, and then if we take derivatives of sine, we eventually get back to cosine. And so having this structure to our guess, b cosine 2t and c sine 2t, would eventually, those derivatives would repeat themselves, and we'd have all possibilities of the structure for this guess at the particular solution. By the way, folks, just a quick reminder, this would not work if this were, say, something like the cosine of 2t squared, because when I take successive derivatives of that, it just keeps getting more and more complicated over the several iterations of derivatives, and I never eventually get back to a form that I've already taken into account when I give the structure of it. So the method of undetermined coefficients does not work for composites of functions. Okay, so normally that would be our guess for what the particular solution would be. But remember that warning that says, hey, you have to take into account, you have to consider the solutions of the homogeneous family of equations. And notice that this left-hand side here is precisely what we solved earlier. And when we gave its general solution, notice we've already got a cosine 2t, and in fact also a sine of 2t in the homogeneous family of solutions. And so that would not get us a solution that's something new. And so what we need is something, a particular solution. And so we need to multiply our guess by a factor of t raised to the multiplicity of the root repeated in the characteristic equation. So although this would normally be our guess, and if somebody gave you some other fourth order linear ODE with constant coefficients, you'd probably be okay with that being your guess for the particular solution. In our case, we need to guess, this is fine because this was not, e to the 3t did not show up in our homogeneous solution. We did have an e to the 2t, but we avoid that. All right, that's good. And so normally our guess would be this. But the rule says to give us give us a solution that avoids those homogeneous solutions, we go ahead and multiply that by a factor of t. Or another way to say that, this would be, our guess would be a e to the 3t plus bt cosine 2t plus ct sine 2t. I'll fix that b. And so this is what we would do the method of undetermined coefficients on. I'm not going to practice that here. You would take two successive derivatives of your particular, or actually you'd have to take four in this case, successive derivatives of your particular solution, plug those four derivatives into the ODE, then go ahead and make that argument of equating like terms together. And if you did so, which I asked a computer to do, we would get A is equal to 5/13, B is equal to 0, and C is equal to 1 over 32. And so that gives us a general solution of y sub t. Remember, this needs to look like the homogeneous family of solutions. So we're going to take our answer from before, c1 e to the 2t plus c2 te to the 2t plus c3 cosine 2t plus c4 sine 2t. All of that is the homogeneous family of solutions that we gave earlier in this video. And I think I might run out of room here. We said that A would be 5/13, then that's e to the 3t, and then B is 0, so we don't have a term there, and C is 1 over 32, and t sine 2t. And I didn't quite make it. But this part right here is our one particular solution to the non-homogeneous family, or to the non-homogeneous equation. And so now we've got the general solution to this fourth order ODE. So folks, you've got some homework problems to work on this. Let me know if you have any questions, but that summarizes what we've done with our nth order linear ODEs up to this point. In the next video, then, we will pick up learning the next method for variation of parameters.